All right, so I'll be going through this quite fast. So if I'm too fast, right, do put out your hand, raise your hand to clarify. Okay, so this is where we left off last lesson. You're supposed to go through the checkpoint, right? Then I've given you the video link for you to check your answers. Eh, these few people? Huh? Okay, don't care. All right, so let's look at this. So for calculation of pH of salt solution, okay, so let's look at work example 8. Okay, so for work example 8, we are looking at the salt. So we are working with the salt and they undergo complete dissociation because they are fully soluble salt. Okay, so between the two salt, you need to ask yourself whether either one of them can undergo hydrolysis. Okay, so this one, do you need me to explain to you how do you decide whether it will undergo hydrolysis? Huh? Do you know how to decide? So you have to check the parent, right? So remember the anion comes from the acid. So this is the ethanoic acid, which you should know is a weak acid. All right, then this must come from your sodium hydroxide, which is a strong base. So having a strong base weak acid, it will give rise to a basic salt. Okay, so because it's a basic salt, I know that it's going to release OH minus. Hence, it must be the anion that reacts with the water to release the OH minus. Okay, so that's why we write the equation this way: proton transfer from your water losing to your A minus. Okay, so because of the OH minus released, then the extent of this hydrolysis is measured by Kb expression. Okay, I repeat myself. Because of the OH minus released, the extent of hydrolysis is measured by the Kb value. Okay, therefore, we carry out this calculation. So of course, since we are working with a base, the first thing we can calculate is the concentration of OH minus, then POH, then finally the pH by taking the difference between 14 and the POH. Can? So there's this additional step when you work with a basic solution. Right, so let's quickly look at the next example. In the next work example, is slightly different or is more complicated in the sense that you are not just given a salt solution, you are forming a salt solution. So in this formation of the salt solution, you have your weak base, the parent is already given to you, and your strong acid, okay, coming together to react together. All right, so from the ICF table, okay, so the purpose of having the ICF table is for you to know what are the initial amount of your acid and base. Then you know that they react in exact stoichiometry ratio. So what you end up with is just a salt solution. So you are forming a salt solution. So this salt, knowing that it's coming from a strong acid and weak base, it will give rise to an acidic salt, right? So acidic salt means what? It will release H+, then it will undergo cation hydrolysis. Okay, so that is exactly what's happening here. Your cation transfer the H+ to your water, resulting in the release of H+. So because it's H+, is measured by Ka, then you do the calculation. Right, so this is what this example is about. Okay, now, like I say, right, this example is more complicated. So notice that there is mixing involved. You are mixing two solutions together. And it's not just mixing, there is a reaction. So notice that when I write a reaction between a base and an acid, I use an irreversible arrow. I need you to pay attention to that. Okay, so the way you write your equation affects how you calculate. So appreciate that having a base and an acid reaction, it is a complete reaction. Okay, but if you're talking about proton transfer, okay, between your weak acid and weak base, okay, with your water, okay, so if it's proton transfer with water in a weak acid or weak base condition, in this case, right, you use a reversible arrow. Okay, so every time you have a proton transfer with water involving weak acid or weak base, reversible arrow. It's just hydrolysis. Yeah, this is hydrolysis. So the acidic salt undergo weak acid dissociation. Yeah, can? Right, so very clear, this is reversible, therefore finally we calculate the pH. Again, sorry. Because it's a complete neutralization process. I mean, it forms a salt, and salt is very stable. It doesn't go back. Can you force your salt to go back to the acid and base? Have you ever seen a salt go stun to go back to the acid and base? Have you ever seen that? Never, ma. So once it forms a salt, it's a very stable product. It will not go back. Yeah, so it's a complete reaction. Can dissociate, but doesn't mean that it go back to your acid and base, right? Yeah, fully soluble. Okay, so let's move on to the next part. Summary for calculation. So this is what you have done for acidic salt. You use a square root. Okay, then for basic salt, you also use a square root. Okay, so please take note. This salt that we are talking about are fully soluble salt. They undergo full dissociation. All right, so I would like you to make this change to your paragraph. They are weak acid and weak bases. Okay, dissociates partially is very ambiguous. Are you talking about dissociation of the salt, or are you talking about the acid or base dissociation? It's ambiguous. All right, so I'd rather you say that they are weak acid, weak bases in water. Okay. Okay, now how come this expression applies? Why are we able to square root this? Huh? What do you think? The H plus and OH minus concentration the same? Are you sure? Is the H plus equals to OH minus concentration? Are they the same? Yeah, so in this case, right, for acidic salt, there is equal concentration of the product form. For example, when anion undergo hydrolysis, there will be a release of OH minus and the weak acid, right? They are formed in equal concentration. So similarly, if you have acidic salt, it will release the weak base and H plus in equal concentration as well. Okay, so if I let both to be X, then this becomes a X squared, correct, in the expression. Okay, so in order to determine the concentration of H plus, that will be concentration of X, then it will be a square root. Okay, I do a lot of shortcut here. You know, before this, you are supposed to come up with the ice table, right? Yeah, but then in the word example, we never use the ice table. But if you can recall, we use ice table when we work with weak acid or weak base. Yeah, so in that ice table, we know that the product are formed in equal concentration. So if I were to find out the concentration of OH minus or the concentration of H plus, I must do a square root. Okay, then after that, right, we notice that for salt hydrolysis is also a small extent. Okay, like weak acid and weak base, they occur to a small extent. So because of the small extent in dissociation, we can make this assumption. The concentration of the salt at equilibrium can be taken to be the initial. Okay, okay, because it's a small extent of hydrolysis. Can I? Huh? No. Why? Why are they equal? This one is the acidic salt. This one is a basic salt. They cannot coexist together. It's either having an acidic salt or a basic salt. I'm giving you two scenarios. Your H plus and OH minus cannot be equal. If your salt is acidic when placed in water, why do you call it acidic? H plus must be more than OH minus, right? Isn't it? When you have an acidic salt in water, why do you call it acidic? There's H plus release. There's OH minus also. Yeah, there is OH minus also, but then are they equal? They are not equal. So what is the difference? If you call an aqueous solution acidic, what does it mean? There's more H plus than OH minus. If you call a solution basic, what does it mean? OH minus more than H plus, huh? Okay, only water at 25 degrees Celsius has equal H plus and OH minus. Water alone. Can? Salt can also have equal. When do you have a salt giving you pH 7? Strong acid, strong base salt. Then you have pH 7. That is also H plus equals to OH minus. Can work. But if you have an acidic salt or basic salt, H plus and OH minus are no longer equal. You must get it correct, huh? Don't get confused, you know. Yeah. The ice table. Okay. So this one, you can place the term initial here because we always make this assumption. Okay. All right. There's no need for you to subtract. You can just use the initial concentration. Okay, can? Okay, I move on, huh? So let's look at checkpoint 8. So you should have done this homework already. Okay, so what's your answer? Denmark? Banana? So do you have your answer, banana? What's your answer? Canada. Okay, why not banana? This is a base. So your pH will be more than 7. Sodium chloride is a neutral salt. So pH equals 7. So does it satisfy this criteria? It doesn't. So B cannot be the answer. Okay, instead C is the answer. Why so? Why so? Sodium chloride is pH 7, right? Do you need me to explain why sodium chloride is pH 7? Strong acid, strong base, huh? Iron 3 chloride is acidic. Why is it acidic? Why is it acidic? You have the base iron 3 hydroxide. So remember, when your N equals to 3, this is a weak base, right? Your chlorine, your chloride comes from hydrochloric acid, which is a strong acid. So when you have a weak base, strong acid combination to form the salt, it will give rise to an acidic salt. So this pH will be less than 7. So it satisfies this criteria. Okay, so hence the answer is Canada. Right? So do you need me to explain anything else? Do you need me to explain anything else? Okay, I move on. So let's look at question number 2. Okay, question number 2, there are 2 things to look out for. Of course, you recognize that you are looking at a salt, right? You are working with a salt. So this means that you need to check for hydrolysis. All right, so ammonium sulfate, does it undergo hydrolysis? Megan, does it undergo hydrolysis for ammonium sulfate? It doesn't? Why not? Sulfate doesn't undergo because it comes from where? Remember, we are supposed to identify the parent. Yeah, so H2SO4. So what about H2SO4? It's a strong acid. Then how about this? Where does it come from? Ammonia. So ammonia is a strong base. Yeah, so weak base. So if you have a weak base and a strong acid, does it give you a neutral salt? It doesn't. So does it undergo hydrolysis? It does. All right. Okay, so it does undergo hydrolysis because it's an acidic salt. Okay, so when you undergo hydrolysis, your ammonium cation will be the one releasing the H plus, okay, and the weak base. All right, so this is the hydrolysis reaction. And this hydrolysis reaction, because of the H plus released, the extent of this hydrolysis is measured by Ka. Are you given Ka? In this question, are you given Ka? You're not given Ka. So is there any way that I can obtain Ka? Yeah, Kb. So in this case, because we are talking about dissociation in aqueous medium, so I can always use Kw divided by Kb to obtain my Ka value, right? So that will be 10 minus 14 over 1.8 times 10 minus 5. So that is how I can calculate my Ka value. All right, then after this, what else do I need to consider? Because how do I calculate this pH? The pH will be equals to square root what? Concentration of H plus is equals to Ka times K times what? Concentration of your salt or ammonium cation here, right? Initial. Okay, so I already know what is my Ka. Do I know the concentration initial? So what is the initial concentration of ammonium? Is the initial concentration of ammonium 0.1? 0.2, very important, because in this salt, upon full dissociation, there is 2 moles of ammonium cation released with 1 mole of your sulfate. Okay, so when you write the dissociation of this soluble salt, recognize that there's 2 moles of ammonium. So the concentration here, because of the 2 moles released, right? Because of the 2 moles released, the concentration here will be 0.1 times 2. Then you substitute and work out the answer. You should be able to get the answer. So for those who did not do anything, please highlight the learning point. You need to consider the mole ratio of the salt. Okay, number 2, you need to know how to get the relevant Ka or Kb value if it's not given. Can? So 2 learning point. So you do this calculation at home, you should be able to get the answer. Class, you're supposed to prepare this. Some of you did not do it. You should do it. Okay, buffer solution. So buffer solution, what is the purpose of having a buffer? Is to resist changes in pH. And how does it do it? By removing small amount of acid or base added to the system. Okay, so there are 2 types of buffer that you need to work with. Okay, so one is acidic buffer. So what are the components of an acidic buffer? It must be the weak acid and the salt or conjugate base. Okay, so the weak acid and the salt or the conjugate base will make up the acidic buffer. And what do I mean by acidic buffer? It will maintain a pH value less than 7. That's the meaning of acidic buffer. It will maintain the pH value less than 7. It can be 6, it can be 5. Okay, up to the system required. Okay, right? So if you have a weak base, right? So how do you form a basic buffer? Basic buffer, of course, will try to maintain pH value more than 7. Okay, so I can make a buffer involving a weak base and its conjugate acid or the salt. So when I have the weak base and the salt, right, then it will help me maintain at a pH value 8 or 9, for example. Okay, depending on the purpose. All right, so very quickly, let's try this. Can the following combination form a buffer? Can the following combination form a buffer? Okay, number 1, HCl and sodium chloride. They are conjugate acid-base pair, right? Can they form a buffer? Cannot. Why not? Yeah, because there's no weak acid, no weak base. To form a buffer, you must either involve a weak acid or weak base. Okay, so this one cannot work. All right, how about number 2? Can it form a buffer? Can it form a buffer? In other words, you must know who are your strong acid and your strong base, so that you can recognize. Okay, so nitric acid and sodium nitrate. This is a strong acid. This is the salt. So can this form a buffer? Cannot. All right, so I hope you recognize that sulfuric acid is a strong acid, but sulfurous acid This is called sulfurous acid. This is a weak acid. Nitric acid is a strong acid, but nitrous acid is a weak acid. Okay, so you can see that the counterpart has one less oxygen. It makes it a weaker acid. Because it's a strong acid and a salt. You must have a weak acid or weak base. Okay, so number 3 is a buffer. Can number 3 form a buffer? Yes. Why? Why number 3 can form a buffer? Because this is a weak base. How do I know this is a weak base? Because it's involving a lone pair on nitrogen. So whenever your nitrogen uses a lone pair as a base, this is a weak base. And this is a salt, right? The conjugate acid. Can? So this combination can form a, what kind of buffer? Acidic buffer or basic buffer? Basic buffer. Okay. Can? Am I going too fast? Pardon again? Yeah. Can? So let's look at the next part. How does a buffer work? So a buffer works by having a large reservoir of the conjugate acid-base pair of a weak acid or weak base. Okay, then it will be there to remove small amount of H plus and OH minus. Okay, now I need you to make a change here. For example, acidic buffer is formed by mixing. Okay, it doesn't just contain this, it's formed by mixing your weak acid and the salt together. Okay, can you help me change that? Okay, so in this mixture, your salt will undergo full dissociation, while your weak acid will stay partially dissociated. Okay? All right? So then what is the difference between a weak acid and an acidic buffer? Because essentially they consist of the same thing, right? You have the weak acid and the conjugate base, which is also observed in a weak acid solution. So what's the difference then? Do you get my question? So how do you think a weak acid differ from a buffer system? How do you think a weak base differ from a buffer system? Okay, so if I use a graph, the diagram to show you, this diagram tells you that if you have a weak acid alone or weak base alone, you see equal concentration of the H plus and the A minus, right? For weak base, equal of the conjugate acid and the OH minus released. All right, but this is not true for a buffer. So what do we do for a buffer? How do we make a buffer? How do we make a buffer? We add salt. So to form acidic buffer, I'm going to add salt. Sodium A minus, my salt. For example, if this is ethanoic acid, then I will add sodium ethanoate. And because of this addition of the salt, what happens to the concentration of A minus? What happened to the concentration of A minus? It will increase, right? Yeah. So now there's an additional source of A minus coming from your soluble salt. All right. And what do you see now? Is H plus still equal to A minus? No longer equal. So same thing, if I were to form a basic salt, I will add, if I were to form a basic buffer, I will add the salt, right? To increase the ammonium concentration. So these two ions here will no longer be equal. Okay, then that is when we form a buffer. Make sense? Okay, so that's the difference between just a weak acid and a buffer, weak base and a buffer. Okay, so can I ask you to copy this now? Very important. Okay, the understanding of this is very, very important. As we start titration curve, this is something that guides you to differentiate whether this is a weak acid or a buffer? Yeah, so when you add salt, there will be additional source of A minus. So your A minus will go up. To make an acidic buffer. Yeah. So to make a basic buffer, then you add the salt also. Yeah. Yeah. It go up, then you make a buffer. That's the essential difference between weak acid and acidic buffer, or a weak base and a basic buffer. Hmm? What again? What this thing explain? So when I add a salt to a weak acid, do you agree with me that the A minus will increase? So when the A minus increase because of the additional source coming from your soluble salt, then this mixture is no longer a weak acid. It has become an acidic buffer. Yeah. So this is what I'm trying to tell you. Yeah. So when you cause an imbalance of H plus and A minus, you form a buffer. Pardon again? As long as they are no longer equal. I never say which one must be larger. Yeah, as long as they are no longer equal, then you form a buffer. Okay, it can be H plus larger, it can be A minus larger, depending on what kind of pH that you want to form. Because different buffer can have different pH value. So you change the pH values by manipulating the ratio. Okay, do I make sense to you? Okay, any other question? Okay. All right. So in this case, right, this is what we meant by a large reservoir. So what is considered as a large reservoir? Your weak acid and the conjugate base, they are almost equal. Okay, so you can see that you have a large concentration of weak acid and also a large concentration of its conjugate base. So that is what we want as large reservoir of conjugate acid-base pair in a acidic buffer. Can? Here. So what do I mean by large reservoir? Must have high concentration of the conjugate acid-base pair, right? Yeah. So how do I create more salt? I add salt, lor. Yeah. Can? Okay, let's move on. So effect of adding acid to the buffer. So this is the equation that you need to show. Because sometimes in A-level question, they will ask you, write equations to show how this buffer system act against pH changes. Okay, so do notice that the amount of H plus will be completely removed by the large reservoir of the conjugate base. Okay, so because there's large reservoir here, therefore it's a complete removal. Okay, remember what I say? All acid-base reaction must be full arrow. This is the acid-base reaction. Okay, there's no water involved in this transfer. Okay, so full arrow. So same thing, when you add small amount of OH minus to the large reservoir of the weak acid, is also a full removal. Okay, so these are the two equations required from you to answer this. Okay, and please take note, the pH of the solution will remain approximately the same. It will not be exactly the same. It will be about the same. Okay, so that is a keyword. It will not remain the same. It doesn't mean that it stays constant. It resists pH change. So there's a slight change. Okay, so checkpoint 9. You're supposed to do this at homework as well, right? Yeah. Okay, so very quickly, this is what you will see. So H plus will be removed by your weak base. Then this is the equation. OH minus will be removed by your ammonium. Okay, then this will be represented by the equation here. Yeah. Any question? Okay, so pH of a buffer solution. Let's look at page 30 now. So an acidic buffer is made out of the weak acid and the conjugate base, the salt. Okay, so I just reiterate again. For acidic salt, for a weak acid, we use this expression. Okay, can we still use this expression when I have a buffer system? Can I still use this? Okay, why is it that we are able to use a square root? Is because weak acid, your salt hydrolysis, weak base and your salt hydrolysis, they give rise to equal dissociation of the products. Notice that this is the trend. They are all equal in concentration. That's why you can use a square root. But in a buffer system, are they still equal? They are no longer equal. So in a buffer system, I add salt. I spend my salt. I spend my salt. Okay, so since OH minus and ammonium, H plus and A minus are no longer equal, I can no longer use this for my calculation of pH for a buffer system. Okay, so for a buffer system, I need to rearrange my Ka expression to become as such. Okay, I can no longer simplify it to be at H plus square. Okay, this doesn't work anymore. This doesn't work anymore. Okay, so this is how it will look like. Okay, the whole expression changes. So if you do a negative log throughout, negative log of H plus, negative log of Ka, and negative log of this, then you end up with this relationship. Okay, and this relationship you can memorize so that you can calculate the pH of a buffer system faster. Okay, so this is called a Henderson equation. Right, so from this relationship, you can see that pH of a buffer depends on two factors. Number one, Ka. As long as the temperature is constant, Ka remains unchanged. Okay, then it also depends on the ratio of your salt and the weak acid, or salt and a weak base. So this is what I'm talking about. The ratio can be adjusted to get the pH value you want. Can? So Megan, do you have any question? You frown a little bit. Do you want to clarify? Huh? Okay, so this is what it's going to look like. So with this in mind, right? So let's quickly look at work example 10. So in this work example 10, you are mixing ammonia and the ammonium chloride. Okay, so these two solutions, there's no reaction. No reaction, so no need to write an equation. Okay, but then mixing gives a new total volume of 50 cm3. So when you calculate the ammonia concentration and the salt concentration, you have to consider dilution. So that's the consequence of mixing. So when you mix two solutions together, you have to consider dilution. Okay, so after you have considered their dilution, you substitute into the expression to obtain the POH first, because this is a basic buffer. Okay, so basic buffer, you work with KB value. Basic buffer, KB value. So the KB value will enable you to calculate POH first. Then you calculate your pH by taking a difference. Can? Right. So can you try checkpoint 10 now? Very quickly. You're going off energy. Biomedical thing. Is it excused by a teacher or? Are you done? Yep.
Is it always for a weak acid will always give a strong conjugate base when it dissociates in water? Oh, and when it hydrolyzes, not dissociates.
Opic acid doesn't undergo hydrolysis.
No. Sorry, strong acid gives a weak conjugate base.
Yeah.
And then strong base gives a weak conjugate acid.
Yeah. Then?
No, I'll just check it. Let me see the shortcut.
Huh?
There is a different. There is a different.
What? What hydrolysis?
I got like my own. I don't use a shortcut.
Okay. All right. So, can I go through the answer to checkpoint 10? So in this case, because you are working with an acidic buffer, so weak acid and the salt will form an acidic buffer. So pH equals to pKa plus logarithm salt over concentration of the weak acid. Okay, so in this case, notice that the concentration of the salt and the weak acid are equal. They are equal. And there's no need for you to consider dilution at all, because it's just giving you the concentration in this solution already. All right. So since they are equal, this means that it's logarithm 1, which is equal to 0. So this means that pH must be equal to pKa. Hence, the answer is 4.74. Can? Okay, this topic is about math, but then before you apply math, you must know what is going on. If not, you cannot apply the correct equation. Okay? So I hope you can recognize that this is a buffer system. Hence, I use this to calculate pH. Right? So this one is forming a buffer. Okay, so this one is forming a buffer by adding the salt and the weak base together. What if, how about this one? So can we try doing this one? Okay, so are you able to calculate the pH of the resultant solution prepared by mixing 40 cm³ of the weak acid and 10 cm³ of the sodium hydroxide? So this is not just mixing, there is a reaction. So after reaction, what type of resultant solution do we form? Then how do we calculate the pH? Right? Yeah.
Because this is a conjugate phase, it won't have a Ka value.
Yeah.
Then so only use this Ka.
Because it's an acidic buffer. Acidic buffer, you use Ka. Basic buffer, you use Kb.
Basic buffer, will they have a conjugate acid?
Yeah. Because it must be a large reservoir of the conjugate acid base pair. Remember?
This one will have the conjugate acid, but it's just not sure.
The acid is the weak acid itself. The conjugate acid base pair differ by 1 H plus. So ethanoic is the base, ethanoic acid is the acid. Huh? Hydrolysis of weak base, meaning it's a weak base, or it's a weak base. It reacts with water, that's hydrolysis. It's a Bronsted Lowry base. So it has to extract a proton. The proton has to come from water. Yeah. I mean, generally we call reaction with water hydrolysis. Generally, yeah. So what kind of reaction mixture do you form here? Is it complete neutralization? Are they added in exact stoichiometry ratio? Yes or no? They react in exact stoichiometry? Yes or no? Yes. Why so? You have equal concentration of the base and the acid, but the volume used is different. So they are added not in equal mole, right? So they are not added in equal mole. So will they completely neutralize each other? So one is in excess. So who is in excess? The acid, huh? So you have the acid in excess. Then you are also, what is the effect of sodium hydroxide here? Yeah, it forms a salt. So in this case, right, in your ICF table, there is a reaction between your weak acid and your strong base to form the salt. Okay, so in the ICF table, you can write something like this. So this is what you started with using the volume times concentration. Okay, so this is the limiting reagent. So being the limiting reagent, it will be fully reacted away. So same thing, this amount of acid will be reacted away. So this reaction will produce this amount of salt. Okay, so finally, when you take the difference, right, in the final resultant mixture, you have 0.003 of the weak acid still left behind. No more hydroxide. This is formed. Ziheng, what are you busy with? using handphone as a calculator. You don't have a normal calculator. Don't you know that acid-base you need calculation? Okay, so in this case, what do you have? You have weak acid, you have the salt, right? Okay, so in this case, is your salt equal to the H plus concentration? Are they equal? Is the A minus equal to the H plus concentration? Why not? Now, if you go back to the idea here, your H plus reacts with the OH minus to form water, right? Yeah. So there will be a drop in the H plus in this equilibrium system. Agree? Yeah. So therefore, according to the Chatelain principle, what will happen? Yeah. So by shifting the POE forward. Okay. So this drop over here will be partially offset by LCP. According to LCP, the position of equilibrium will shift forward. So what does it mean? This will up, right? While this has dropped, but it will only be partially offset. Can see? Okay, I do it bit step by step. So in a weak acid, just having the weak acid, we know that it undergoes spontaneous dissociation. So this will be 0.1, say. This is also 0.1, for example. Okay? Then when I react with a base, OH minus, my H plus will drop, right? So it will minus, say, 0.03 away. So when this drop, well, how would the equilibrium react? Does it stay there? Yeah, it will, based on the Chatelain principle, POE will shift. So when POE shift, what you can only offset is partially. So it will not top up the 0.03, it will only partially offset the difference. Okay, so this will mean that this will add 0.02, for example. Okay, so do you recognize that the resultant mixture will have a lower concentration of H plus than before, while the A minus will be higher than before. So with this, right, these two concentrations can no longer be the same. Hence, a buffer system is formed. Can? All right, so this is what we are talking about here. So if you calculate the pH, right, pH will work out to be 4.27. Do you have that? Okay, so we are forming an acidic buffer because there's still unreacted weak acid in the system. Okay, so this is the amount of salt that is formed. This is the amount of the weak acid unreacted. Do you know why I do this? What's the purpose of 1000 divided by 50? To convert to concentration. Yeah, so basically this purpose here is to convert to concentration. And this concentration here is in a new total volume of 50. Yeah, so you are adding two solutions together and these two solutions undergo a reaction. So the total volume now is 50. So the salt is formed in a total of 50. The weak acid left is also in a total of 50. Yeah. And what do you see? They can actually cancel each other out. So essentially, right, the ratio of concentration is the ratio of the number of moles. Can you follow me? Because this part and this part can cancel. They are swimming in the same total volume. Yes? Again, sorry? 0.003, because we have an ICF table. I don't know whether you have seen this part because you went toilet for some time. Yeah?
Wait, can you explain this part again?
This part?
Yeah, I don't understand what that is.
Okay, please take note, in this ICF table, what are you working with in terms of mole or in terms of concentration? In terms of mole, right? But when you substitute into your expression, they are all in the form of concentration. Agree? So now, after adding the 40 cm cube and the 10 cm cube together, the total volume is 50. So this is the amount unreacted 0.003 of the weak acid in a volume of 50. But then this one is cm cube. How do you convert the concentration? Times 1000. Divide by this volume times 1000. Because your concentration is always mole per dm cube. Mole per dm cube. Yeah, so you divide by 50 to get mole in 1 cm cube.
Okay.
Yeah, can All right, any other question about this? Any other question about this? Okay, so with this, right? With this, there are two ways to increase the concentration of salt. Then I would like you to copy this down, this paragraph down. Can you help me copy this down? There are two ways to increase the concentration of salt. One will be just stem the salt. Okay, another way will be through an acid-base reaction. And this is exactly what you're going to observe when we start the titration curve. Okay? Can I move on? All right, so buffer capacity. So in order for a buffer to be more resistant to changes in pH, the concentration of the acid base and the salt, the weak acid and weak base and the salt must be large. Okay? So we have this criteria. Then the buffer will be operating at the maximum buffer capacity when they are exactly equal to 1. Okay? It's a ratio. Remember this expression? So we are talking about this fraction. Okay, so this fraction in the ideal case should be equal to 1 for maximum buffer. Okay, so when it's equal to 1, then pH will be equals to pKa, pOH will be equals to pKb. Can? Any question at this point of time? Right, so very quickly, right, I would like you to consider this scenario. So what do I mean by small amount? Okay, so let's say, right, in my buffer system, I have concentration of the salt, 0.1 mole per dm cube. Then concentration of the weak acid, also 0.1 mole per dm cube. And this is the equation we write to show the complete removal of the small amount of H plus added, right? Okay, so when I say small amount, it can be 1% of the weak acid. Okay, so 1% of this weak acid is 0.001. Agree? So when I say small amount is relative, relative to the concentration of the weak acid and the salt that is present in the system. So when we take just 1% as the small amount, then I will have this, correct? Yeah, so this will be completely reacted away by the large reservoir of your conjugate base. So this will be reacted away, then this will drop. Agree? According to this equation. Your A minus, your conjugate base is the one that removes the H plus. Therefore, the conjugate base will drop. Drop by how much? Drop by the amount required to remove the H plus. So the H plus is 0.001. Your conjugate base will drop by 0.001. Then what will happen to the weak acid? What will happen to the weak acid? It will increase by 0.001. All right. So how do you calculate the fraction now? When you substitute it back, right? What happens? Logarithm, the salt becomes 0.999, while the weak acid becomes 0.101. Do you see that there is an adjustment in the fraction? When the fraction is adjusted, is your pH value affected? Yes, it does. That's what we meant. pH is approximately the same, but never constant, because this fraction changes as it removes the H plus or the OH minus that is added to the system. Okay? Yeah? Okay, so one of the tutorial addresses this part. Okay, so that's why I'm showing you the calculation here. Tutorial question asked. Right, so with this, I end my lesson. Okay, so this part you can read on your own. Then please, try your best to complete checkpoint 11 as your homework. Okay, then I'll start the titration tomorrow. Okay, so today your homework is just checkpoint 11. 3 questions. Can?